All right, let's talk about a mystery that I'm pretty sure has haunted every single one of us who's ever worked with data. It's that sinking feeling you get when your perfect model just fails. You know the drill, right? You've spent weeks, maybe months, building a model. It absolutely crushes all of your tests. The scores are brilliant, so you push it out into the real world feeling like a genius, and then it just falls flat on its face. It's so frustrating. But what if I told you this isn't just bad luck? What if it's a predictable statistical trap? Well, this whole phenomenon actually has a name. It's called the winner's curse. And it feels a bit like magic, or maybe some kind of curse, but the explanation is actually just plain old statistics. See, the very act of selecting a winner from a bunch of different options is what tricks you into thinking it's way better than it actually is. So here's the absolute heart of the issue. When you line up all your models or all your different hyperparameter settings and you pick the one with the best score, that score is almost certainly an illusion. It's inflated. You think you're picking the best model, but what you're really picking is the model that got the luckiest on your specific set of test data. Now, this quote looks a little mathy, but stick with me, because it really boils it all down. It's a simple way of stating a principle called Jensen's inequality. And all it really means is that the best score you see from your winner is pretty much guaranteed to be higher than the true, real-world performance you can expect. You've basically created your own optimistic illusion. So let's pull back the curtain on this illusion. How does this happen? Why do we get this optimistic bias? And more importantly, what are the things that make it even worse? And that brings us to the official term for this, optimistic bias. Really, all this is the gap, right? The gap between that incredible score you saw in development and the, well, less incredible score the model gets in the real world. It's the painful difference between what you hoped for and what you actually get. This slide just lays it out so clearly. On the left, that's the awesome score you see from the winner of your model competition. But on the right, that's the true score you should expect. And because of just random noise and luck in your data, the score on the left is almost always going to be bigger. You've been cursed by your own win. So what makes this curse even more powerful? Well, it's usually three things. First, if your dataset is too small, random luck just plays a much bigger role. Second, the more models you try out, the higher the odds that one of them is going to look amazing just by pure chance. And finally, if the way you're even measuring performance is noisy or has high variance, well, that's just throwing gasoline on the fire. Okay, to really solve this mystery, we have to understand the main characters in this story. Let's call them the suspects. These are the algorithms we use to make choices, and they come in two flavors, selectors and meta-selectors. First up, we've got the simple selector. You can think of this one like choosing from a fixed menu. You've got, say, 2 or 3 models that are already built, already trained. The selector's only job is to look at how they do on some data and just pick the winner. That's it. Simple. But let's be honest, that's not usually what we're doing. More often, we're using a meta-selector. And this is where things get really powerful, but also where the winner's curse can be incredibly dangerous. A meta-selector isn't just picking a final model. It's picking the entire recipe for building the model. It's deciding, should I use a random forest or a neural network? Or what are the absolute best hyperparameters for this XGBoost model? Here is the perfect way to think about it. A selector asks, of these cars already sitting in the parking lot, which one is the fastest? A meta-selector asks a much bigger, more fundamental question. Which car factory is the best at building fast cars? And you can see how most of what we do in machine learning is really a meta-selection problem. So now we know our suspects. Let's head over to the scene of the crime. The most common mistake, the place where almost everyone gets tripped up, is what's called the single loop trap. And here it is. This is the big one. The critical mistake is running a single big cross-validation to test everything, finding the algorithm with the best average score, and then reporting that very same score as your final performance estimate. You see the problem? You've used the exact same data to both pick the winner and to judge how great that winner is. The selection process has totally contaminated your evaluation. I mean, listen to this quote from the source material. It says it all. Even a powerful standard technique like leave one out cross-validation becomes very, very over-optimistic the second you use its results to pick a winner and then turn around and claim those same results are proof of how well it works.
Okay, so we've looked at the problem, we know what causes it, we know the big mistake to avoid. So how do we actually fix this? How do we defend ourselves? We need a much more robust approach to get an honest answer.
And the solution is actually really elegant. It's called nested resampling. Now, I know that sounds kind of complicated, but the core idea is actually super simple. You just create two loops, one inside the other. An inner loop handles the selection, and an outer loop handles the evaluation. They each have one very separate, very important job. The outer loop has one and only one purpose: to give you an honest performance score. It starts by splitting your data and hiding a piece of it away. That's the outer test fold. This piece of data is sacred. The selection process will never, ever get to see it. The outer loop then hands the rest of the data to the inner loop and just waits. When the inner loop comes back with a champion model, the outer loop finally tests it on that fresh, completely unseen data. The score you get here, that's your real, unbiased estimate. So while all that's happening, the inner loop is where the big competition takes place. It takes the data from the outer loop and runs that huge bake-off, your cross-validation to compare all your algorithms and hyperparameters. It finds the winner. But here is the most important part. The performance scores generated inside this inner loop, they are used only to pick a winner. That's it. They are never, ever reported as the final result.
So I know what you might be thinking. This sounds like a lot of extra work. Why bother with all these loops? Well, because this isn't just some fussy academic detail. This is about building models that you can actually trust in the real world. Honestly, it's about your credibility.
So let's just quickly recap the big wins here. Using nested resampling gives you a truly honest, reliable performance estimate. It helps you avoid shipping a model that looks great on paper but is basically doomed to fail. And really, what you're evaluating is your entire process for selecting a model, which is so much more powerful. Ultimately, doing things this way is how you build real trust in your work and your results.
And you know, this whole idea goes so far beyond just machine learning. I want you to imagine this. 100 different medical labs are all testing a new drug. 99 of them find nothing interesting. But one lab, just by pure random chance, gets a result that looks statistically significant. They publish it as a breakthrough, the media goes crazy. That right there, that is the winner's curse playing out in science, with potentially huge consequences for all of us.
And that kind of leaves us with a pretty big question, doesn't it? The next time you see a headline about some amazing new discovery or revolutionary new model, it's worth taking a second to ask yourself, is this a real breakthrough? Or are we just seeing the winner's curse in disguise?